to take a closer look at this new topic called regioselectivity. And first we're going to look at regioselectivity of chlorination. But first let's talk about equivalent positions in hydrogens. So I want to take a look at these two structures up here at the top. So how do we determine equivalent hydrogens? Well, one of the easy things that we can do is we can take off an H atom and put on some other atom, like how about a bromo group? It could be anything. You could call it an X, and see if it's a different product. So if it's unique, or if it's identical to taking an H off of another position. So an easy way of kind of starting off with this is to look at methane. So if we took off this H right here and replaced it with a bromo group, we would have this. Right? If we took off this H and replaced it with a bromo group, you would have this. Now those two molecules are the same, right? We can rotate them around and they are superimposable. They're the same molecule with the same name. Now, same thing down here below. So we would say here that this has 4 equivalent H's. Right? When we look at ethane, these H's at the end are equivalent to each other. So how can we figure that out? Well, let's take one of those H's off and let's put a chloro group on there. So going to line structures, that's what that would look like. Right? If we took one of the H's off of this end and put a chloro group, it would look like this. Right? So this is 1 chloroethane, or just chloroethane, and this is also chloroethane. So those are the same name, same molecule, right? So let's take a look at this molecule, propane. And let's take a look at this position first. So what would happen if we took one of those H's off and let's replace it with a chlorine atom? So chlorine, CH2, CH2, and CH3. Well, what's the name of this thing? 1 chloro propane, right? So we can see also that any one of those 3 H's would give you 1 chloropropane, right? So those 3 H's are equivalent to each other just by the fact that they're on the same carbon. Now if we take a look at this, we'll label this B. Let's come over here and let's write down what we would get. That would be a CH3, CH, chlorine, CH3. What's the name of this? Well, that's a 2 chloropropane, right? And then we'll label this C. Right, so we have our A atom that we dealt with. We have the B, and now we have C. So as we go through and look at C, that would be CH3, CH2, CH2, and then a chloro group. What's the name of this? Well, this is 1 chloropropane. And of course, all 3 of those H's are equivalent. They would give you 1 chloropropane. So this, right, and this guy down here are the same. 3 H's here, 3 H's there. That means 6 H's are equivalent at that position. And of course, these 2 H's are equivalent to each other too. So those are 2 H's. Right? So this is going to matter for us when we look down here below. Now, by the way, because we can put a chloro group either at position A or really B, right? A and C are equal to each other. We can get 1, 2 different outcomes. And those outcomes differ by where the chloro group is. So they're called regioisomers of each other. Now, let's look at the regioselectivity of chlorination. So when we look at that molecule, we can put in information that we gathered from up above. So we said that this and this were equivalent to each other. So there's 2 CH3s, right? That has 6 hydrogens on it, okay? And then we have 1 CH2 that has 2 hydrogens on it. So the ratio is a 6 to 2. Right? That's the same as a ratio of a 3 to 1. So if it was purely statistical and we just randomly could pluck off hydrogens and throw on a chloro group, then we're more likely to get products that have the chloro at the ends in the middle because there's more H's there. There's more opportunities, right? 6 opportunities versus 2 opportunities. So let's go through and let's look at the experiment. So you go through and you carry out this experiment, right? You put a little bit of light in here to get the reaction to occur. And what you get is 1 chloropropane. So how much do we expect to have? Well, remember the ratio was 3 to 1, right? So that means that we have a 3 out of 4 chance, right? Because there's 4 total. So there's a 3/4 chance and a 1/4 chance there. So a 75% likelihood of it occurring at that position. Well, 2 chloro, 1/4 of the time, or 25%. Now, we compare this with the experimental result. The experimental result here is 40%, 60%. So it's interesting. This should make you scratch your head because look, we expect more right here, but actually we got more down here. So we got more of the product that we expected less of. So the experimental percentages do not match the expected percentages, right? Therefore, when we look at this, not all H's are equally reactive, right? So there's a factor that we have to kind of consider here. And it's interesting the way that we can calculate this. So we can calculate relative reactivity. Right? So when we go through and look at this, if we look at a primary position, right? So primary position, 40% is what we got experimentally, right? That's what we get through our experiment. There were 6 H's that were primary. The primary position is that CH3 connected to that CH2. That's primary. And that's primary, right, guys? So 6 H's. So we divide that out, and that's 6.67% per H atom. And then we can do the same thing for the secondary. The secondary position here would be this fellow right here, right? So experimentally, we got 60% there, right, from that table up above. And when we look at the structure, there's only 2 H's. So that's 30% per hydrogen there. And then we can look at this ratio of a secondary to a primary, and that gives us the relative, it gives us a factor, right? A relative reactivity factor of 4.5. That's secondary to primary. So going from primary to secondary to tertiary, right? 4.5 times more likely to put a chloro group at a secondary position, 5.5 more times likely to put it at a tertiary position compared to your primary position here. So you guys should be familiar with this table. This is important for us to know. Now that's a big enough difference, right? If you think about it, well, if your salary is 1 and you multiply your salary by 4.5, you're pretty happy with that, right? That's pretty wonderful. But it's not big enough of a difference for us to only write tertiary or secondary products. So chlorination is actually going to occur at primary, secondary, and tertiary positions, even though there's a discrepancy in reactivity here, right? The relative reactivity. Let's look at some BDEs for chlorination. So I tried to make this nice for us so we didn't have to write down a bunch of stuff. So here is this molecule, and this molecule has a primary position. So here's our primary position. It has a secondary position in it, and it has a tertiary position in it, right? That's the tertiary position. Here's the secondary. Here's the primary. And then from a BDE table, we have a BDE of 98 for this primary, 95, and 91 for tertiary here, okay? So remember, BDE is broken minus formed. That's what we break minus what we form. And in every one of these propagation step number 1s, we break a carbon-hydrogen bond, and then we form HCl, right? So that's formed for every one of those possibilities, for the primary, the secondary, the tertiary. Okay? So again, if we look at this thing, what we're doing here is we're coming over here and looking at pathway A. So this is like this is our A here. Right? So here's our pathway A right now. And that puts a radical here at our primary position. So if we look down below right here, that's for our pathway A. The BDE for this is 98 minus 103, which is negative 5. Okay. Now, as we look at secondary, so what's secondary? So secondary here is our pathway B. So here's our pathway B right here. So that's forming a radical here at the secondary position. And then still our BDE of HCl is 103. So now we're going to take 95, right, because that's our broken. And we're going to subtract that from 103. And that's going to give us negative 8. So we're a little bit more exothermic there. Right, now we have to look at our next pathway, which is pathway C. So here's our pathway C here. Right, BDE 91. So we're coming down this direction. Right, and that's going to put our radical right here. And again, 91 minus 103, negative 12. Okay, so tertiary is the most exothermic here. It also turns out that it has, we're going to see this, it's going to have the lowest activation energy, and hence it's going to be the most reactive. So what we'll do is we'll come back in a minute and we'll put all these numbers together, and we're going to look at how the activation energy relates to each of these. So it turns out to be a little bit different for each one. Now, one of the reasons why, and I want to just plant this in your mind, is look at the radical stability. Here's a primary radical, right? Here's a secondary radical. Well, here's a tertiary radical. What do we know about that? We know that tertiary radicals are more stable than primary radicals. So it makes sense that it would have a lower activation energy, and because of that, it's easier for this reaction to take the path of least resistance, which is the pathway with the lowest hill to climb over, right? That activation energy. So we do see that tertiary are more reactive than secondary, which is more reactive than primary.